We're on our second talk for today, again in France. So today is the spotlight on French startups. We're going to be looking at French quantum startup Alice and Bob. So welcome. Final year PhD student in theoretical quantum physics within l'INRA quantum team in Paris and the Alice and Bob startup. Her work focuses on superconducting qubits, Hamiltonian design engineering, and simulations. She joins us today to give us an introduction to cat qubits. So if you didn't have a chance to look at some of the pre-session reading lists on Canvas, a cat qubit is a type of qubit named after Schrodinger's cat. And this session is going to be incredibly fun. And I will hand over to you now to kick things off.
Thanks for the nice introduction and for giving me the opportunity to introduce cat qubits. I really like to talk about cat qubits. I'm very happy to be here today. And yeah, when I signed up for giving this talk, I was in my final year for a PhD as a PhD student, but now I'm finally a PhD. So I have defended my thesis a month ago. And I worked on cat qubits, a very specific type of design of cat qubits. I will not talk about that today. I think it's going to be a really nice and slow introduction about cat qubits because they're not that famous. I mean, it depends on who you talk to, but they're not that famous when I speak to the community. So I'll talk a little bit about why they're interesting and what they are. And then I'll talk about physically, how do we engineer them? How do we implement these cat qubits? So yeah, I'll dive in. So first of all, I'll be talking about what cat qubits are and then going a little bit to what classical and quantum bits are. I'm pretty sure the audience is familiar with this, but to give context, we know that classical bits have two states, either 0 or 1. And then we have only one type of error that can occur in these types of qubits. And the error rate per operation is very small. So we have very rare events of errors occurring on classical bits. And then if we try to compare this to quantum bits, we now have this representation of a block sphere. We have these two dimensions. We have our quantum state zeros of the zeros and the ones around all this block sphere. And now the particularities that we have these two dimensions, this block sphere, and then we have errors that can be projected on either bit flips or phase flips. So we have two types of errors to deal with right now. And even worse than that, the error rate per operation is very big if I compare it to the classical one, which means that if you want to do reliable quantum computation, then we need to find some sort of strategy to deal with this. And one way to deal with this, one common approach, is to encode information redundantly, what is known as quantum error correction. So instead of having one physical system, one two-level system, what we're going to do is we're going to take several physical systems and take the bunch of physical qubits as only one logical qubit. And what we're trying to do here is we're trying to make the Hilbert space larger, bigger than just two-level systems. And we use this extra degrees of freedom in order to do quantum error correction. So the abstraction of this is that now we have this logical state 0, logical 1 of this whole logical qubit comprising of several physical qubits. And then we encode information in this logical code space. And then we have this error space where when errors occur on this code space, then they go to this error subspace, but then we can detect them and correct them back to the code space. And so we can have errors occurring on the physical qubits as long as we have some sort of code to correct them on the logical level. So what's important is the logical level. So this, for example, is one way to do it. And for example, it's if you're familiar with surface code or codes like that's what we're trying to do. We're encoding information redundantly, making the Hilbert space even bigger. However, there's another way in which we can make the Hilbert space bigger. And this is what's interesting for us. Now, instead of having several two-level systems that make the Hilbert space bigger, we take only one physical system, which is going to be a harmonic oscillator. And we're going to take advantage of the infinite dimensional Hilbert space of this one qubit, of this one, for now it's a harmonic oscillator, right? And we want to encode information in this infinitely dimensional Hilbert space and take advantage of this extra infinite degrees of freedom that we have to do the error correction. So now the abstraction is the same as the one we had earlier. We have this code space. We need to find a way to encode logical information in this harmonic oscillator, but once we do it, then we have our code space, and then we have the error space that we can do error correction again. And so this is the paradigm, this is the picture that I want to give of how different it is to use bosonic codes, and qubit is a type of bosonic codes compared to more standard two-level systems. And so going further, now I'm going to be interested in a type of bosonic code that is called the CAD qubits. And I'm also going to focus on the platform of superconducting circuits. So there's many ways to work with harmonic oscillators, but the platform that we work with is superconducting circuits. So what we want to do is we have this harmonic oscillator that can be a cavity mode if we look at it in the optics kind of picture, which is a photon that's trapped between two mirrors, and this cavity has the particularity of having the resonant frequency at a certain resonant frequency. Here it's omega A, so I call it mode A, cavity A. And then equivalently, if I look at the superconducting circuits, then an LC resonator also behaves as a cavity. So we have microwave photons now, but still electromagnetic waves, still photons going back and forth in this LC resonator. And then we can look at the energy of the photons inside this resonator that can be described by this Hamiltonian, where omega A is the resonant frequency of this resonator. A dagger A are the creation and annihilation operator. This is the basic quantization of a harmonic oscillator. And so when we look at the energy levels, then we have this infinite Hilbert space, where we have here vacuum zero state, Fock state 0, Fock state 1, Fock state 2, etc., until infinity, and they're equally spaced by omega A energy, h bar omega A. And so the way we're going to encode information in this infinitely large Hilbert space is by using coherent states. So if you're not familiar, they're a sum of Fock states, and there's a Poissonian distribution in them. And then if you want the physical explanation, basically these were created because they're very close to a classical state produced in a cavity mode. So if you drive a cavity mode with a classical tone, it's going to directly create a coherent state. So these are actually experimentally more easy to create and to deal with than Fock states. And so we have these coherent states, and what's also going to be interesting is that these coherent states, if we look in the phase space, there's this Wigner representation in phase space, and they can be illustrated in this phase space. So a coherent state is going to be a Gaussian distribution in phase space. So vacuum is going to be in the middle here, and then a coherent state plus alpha is going to be vacuum displaced to the right. And then a coherent state, alpha is a complex number, so a coherent state minus alpha is going to be vacuum displaced to the left. And then in this phase space, we can choose a basis to encode information. And here I'm going to talk about the two-legged cat qubits, so this basis that I'm showing here. So the logical zero is going to be this coherent state displaced to the right. The logical one is going to be this coherent state displaced to the left. And then a bit flip is going to be flipping from plus alpha to minus alpha. And then we have coherencies, which are basically alpha plus minus alpha and alpha minus alpha. And then we see here the fringes in the middle. They're basically the coherencies between these two states. Now we have like this picture that I showed earlier, where we had this two-level system where you encoded 0, 1. Here we're encoding it in this infinitely large Hilbert space, but still we can define what the logical 0 and logical 1 is. And then we have this familiar picture of the Bloch sphere. And then the question we can ask ourselves is, why are we trying to encode things in this way? Is because, as I just said, we have this, in this phase-space picture, this bit flipping from alpha to minus alpha. And then you have the phase flip, which is flipping to plus logical to minus logical. And the particularity of cat qubits is they are biased noise qubits, which means that if I look at this picture in the phase space, where I have this state with a superposition alpha minus alpha, and I increase alpha, increasing alpha amounts to increasing the number of photons that I put in the cavity. So the larger the number of photons I put in the cavity, the bigger the overlap between these two states is. And so because they are farther in phase space, the overlap between these two states is getting smaller and smaller. And so the probability of having the state flip from minus alpha to plus alpha, the opposite, so from logical 0 to logical 1, gets smaller. And because it's a Gaussian distribution, it's exponentially smaller, which means that the rate of bit flips from 0 to 1 and 1 to 0 gets exponentially suppressed with the number of photons that we put in the cavity, which is good news. Now we have a way to inject more photons in a cavity, right? And making the bit flip of these qubits that we encoded exponentially suppressed, so getting smaller and smaller with the number of photons. Adding photons is an easy task. And the price we have to pay for that is we have a linear increase in phase flips, so flipping from 0 to 1. But then we can think of these qubits as if we have this autonomous suppression of bit flips, it's as if we can almost forget about bit flips and we only need to care about phase flips. So it's as if we go back to this classical picture where we have only one type of error that we care about. And so this has been experimentally shown. So here we have the bit flip time. So it's the inverse of a rate. And the time gets bigger, exponentially larger with the number of photons that we put in the cavity. And then now we have the bit flip rate where we see the linear increase. And this has been shown in several works by Alice and Bob, by AWS. And so this is some proved exponential suppression of bit flips. And so why is this interesting? So as I was saying earlier, the standard way to try to do quantum error correction, there are a lot of different codes, but the most common code is the surface code, and is what Google is using, for example. So when we have this, so a transpond is a two-level system. When we have this standard two-level system surface code, we have this grid where we can correct for errors. We can imagine these two dimensions where one dimension is correcting for bit flips and the other dimension is correcting for phase flips, right? But now, because we only care about the phase flips that are left to be corrected, instead of doing this big surface code with a lot of qubits, what we care about now is only one type of error. So we could use concatenate this cat qubit with a repetition code and correct for both errors at the same time. And just to give orders of magnitude, for example, for the Shor's algorithm, you can find this information in this paper from people working at Alice and Bob, where if you use the standard surface code, then you need 20 million qubits to factorize the RSA integers. But for a cat qubit, for doing exactly the same operation, then you would need much less qubits. So you reduce the number of qubits by 60, which is huge if you're thinking about hardware efficient approaches. So basically, this is the motivation of why we're interested in cat qubits. And now I'm going to quickly tell you about how do we engineer a specific type of cat qubit. Again, I'm going even deeper, the dissipative cat qubits. And so basically, the image is if we want to stabilize an alpha state, so a coherent state in a cavity, if we have a continuous input of one photon drive, And then naturally, the cavity happens to have one photon dissipation. So basically, naturally, a cavity, when you design it, it still has photons leaking one by one. This is the natural process of a cavity. And then you drive it with a one photon drive. So you put photons one by one in the cavity. Then if you look at the dynamics of what this does inside the cavity, then it stabilizes an alpha steady state that we can control, because we can control this one photon drive that we put in the cavity. And this alpha steady state is going to be the steady state of the dynamics of the Hamiltonian and the dissipator that are happening in this dissipation, in this cavity. And so we have this competition between energy input and dissipation that stabilizes the state, right? But here it stabilizes only one state, which is the plus alpha or whatever state you're stabilizing with your drive. But we want to stabilize two states, plus alpha and minus alpha. So what we're doing instead, we're going to need to do is we're going to continuously inject photons in pairs through a two photon drive and allow for a two photon dissipation. So now from this cavity, photons are injected and dissipated only 2 by 2. So you can only go from 0 to 2, 2 to 4, but you cannot go from 2 to 1. So you prohibit having one photon exchanges. And when you look at the dynamics we describe this dynamic, so you have this Hamiltonian that injects photons 2 by 2. We have this dissipator that dissipates photons also 2 by 2. So the A square is for that. The steady state of this dynamic is going to be alpha steady state square here. So the plus alpha and the minus alpha are steady state of this dynamic. So now by continuously driving 2 by 2 and having dissipation 2 by 2, we're stabilizing these two states, which is exactly what we want to do. We want to stabilize plus alpha, minus alpha. And so not only are we stabilizing these states, but we're stabilizing also all superpositions of plus alpha and minus alpha. So we have also the coherences that are protected by this dynamic, basically. So, however, this kind of two photon dissipation, so basically, like these equations are equivalent to having this jump operator, which basically says your cavity only exchanges photons, only loses photons 2 by 2 around the steady state alpha with the environment. However, this kind of two photon dissipation needed to stabilize the cat state is not naturally occurring in typical cavity resonators. Photons usually lose photon loss happens one by one. Therefore, we must induce this two photon dissipation artificially through specific circuit elements and nonlinear interaction. We can engineer these types of interactions. We cannot engineer directly how the cavity interacts with the environment. What we can do instead is we add a second mode that we call the buffer mode. So now we have this memory cavity that's going to hold the cat state. That's a high Q cavity. So it means that it almost doesn't lose photons one by one. So we forget about the one photon dissipation. And we want to engineer the fact that this cavity can exchange photons only 2 by 2 with this buffer mode. And this we can engineer because we can engineer interactions between two cavities in superconducting circuits. And now this buffer mode is going to be most of the time empty. So it's going to lose photons one by one with the environment, which is the natural thing that happens. And by driving this buffer mode and engineering this two photon exchange, now we have equivalently this Hamiltonian, where you see that we have two photons created in the memory mode are destroyed by one photon in the buffer mode. And so this Hamiltonian is going to stabilize the cat states that we wanted to stabilize earlier. In order to do so, we need some nonlinear coupling, and because we're doing superconducting circuits, we have this nonlinear element that is called the Josephson junction, if you're familiar with superconducting circuits, that can make this two-photon interaction happen. So by engineering these types of circuitry, putting elements together, putting the right drives and tones, we can stabilize cat states, and this is what is done experimentally. I'm not sure how I'm doing on time. I think I had an additional slide, but maybe I'm just, okay. So basically what I want to say is that this two-photon exchange is equivalent to having this two-photon dissipation that I was talking about earlier. And this two-photon dissipation stabilizes the cat state. And this is how we do it experimentally. And here I will just flash one type of circuits. So this is the kind of the illustration, cartoonish illustration of what we do. But then in reality, the things that we engineer are circuits. So we have this resonators, we have these Josephson junction elements, we have this time-dependent Hamiltonian, and then by putting the right tones, the right drives at the right places, we have effective Hamiltonian that does exactly what we want, which is exchanging two photons from the memory mode with one photon from the buffer mode and vice versa, which allows us to stabilize cat states. And here, I think I'm talking for about 20 minutes, so I'm going to stop and take some questions. Okay.
Thank you so much. We've got some questions coming in via Discord that I can read out to you, and I'll post them in the chat as well so you can see them.
Perfect.
So we have one from Canada, and the question is, are the error space mechanisms for correcting errors quantitatively different from classical Hamming code?
I'm reading again the question. Are the error space mechanisms for correcting errors? The first thing that comes to mind is redundancy. I think, okay, I'm not sure I understand fully the question, but I think like qualitatively, this is a shift of paradigm. So I think the question is about how cat encoding is different from normal types of codes, normal types of encoding, like Hamming codes or something different. So basically, like the most important thing is now where we have two different paradigms where we can either encode information in two-level systems, or we can encode information in infinite Hilbert spaces and then use this type of continuous or analog systems to encode information and do the error correction. So these are really different types of ways to do redundancy. The usual way is by doing it with a two-level system and surface code. Here we're trying to really use only one physical system and encode all the information in the infinite ladder of the physical system. Yeah, maybe we can discuss this even later more on Discord to understand really what the question was about.
Thank you.
Okay.
Now from Ron in Chicago, who is asking, what is the difference between a cat qubit and qubits?
Yeah, so here what we're not doing qubits. We're not trying to have like quantum systems with 3 or 4 or whatever, how many you want levels. Cat qubits, in the end, you still have a qubit with effectively one logical 0, one logical 1. You don't have more levels. You're using the infinite level of the Hilbert space to encode, in the end, a logical state that has logical 0, logical 1. There's no 2, 3, 4. There's just logical 0, logical 1. And then you do gate-based quantum computation, as you usually do. But this is not qubits. This is really taking advantage of the fact that you can use the harmonic oscillator to encode information in a different way, in a continuous way, different from the digital one. Qubits would also be finite dimensional way system. But here it's an infinite dimensional system. You're using all the ladder of the Hilbert space to encode information. So it's a different, so the philosophy is more for two-level systems, you have your two-level systems and then you scale to do the error correction. For bosonic codes or for cat qubits specifically, you construct the error correction directly in your qubits, and then you can scale it to do more error correction. But the error correction is directly designed when you design your qubit, and the cat state autonomously corrects for this, autonomously is doing error correction already compared to the two-level system point of view.
Thank you.
Another question.
Yeah.
So the other question is, are the two photons in a two-photon drive the same frequency? Yes. So frequencies are important here. We're trying to input photons 2 by 2 at the same frequency, which is at the frequency of the memory mode. And then because we add the buffer mode, you have also the frequency of the buffer mode. And an important, can you still see my screen or not? Yes, I think you can. So here, for example, in this view, oh, okay. So we have these two photons have the same frequency because they're photons either entering or getting out of the memory at frequency omega A. And then the photons going out of frequency omega B have the frequency of the buffer mode. And then basically omega B and omega A and twice omega A, they don't have to be the same. We can add a tone to match this frequency condition, to satisfy this frequency condition. But basically these two photons are coherent photons. They have the same frequency and they're going in and out at the same time. Okay. When one increases the number of coherent photons in the so the question is, when one increases the number of coherent photons in the cavity, basically the quantumness of the underlying phenomena. I wouldn't say you're increasing the quantumness. So if I would say more, you are making the overlap between your two states smaller, meaning that you have less, you could call it tunneling, that happens between the state plus alpha and minus alpha. The quantumness is given by the negativities in your, so in your phase-space representation, the red is going to be positive and the blue is going to be negative. And the more you have negativities in your phase-space representation, the more quantumness you have. If you have only red, so only positive things, then you have a classical state. And so by increasing the number of photons, basically what you're doing is you're making these two blobs farther from each other. It's not a question of quantumness, it's a question of overlap between these two states. Even if we forget about these fringes and we have just a plus alpha and minus alpha state without any fringes in the middle, then having suppressing bit flips happens by increasing this, even if we see it as a classical bit. By increasing how far these two states are, we're still suppressing bit flips. Yeah, I think that was the last question, right? Okay, thanks a lot for all your questions, guys. And also available on Discord if you want to discuss further.
Thank you so much. That was an awesome talk, and
Thanks a lot.
I will tag you on Discord in the channel where we've got the kind of questions coming in, as
Perfect.
well, so you have visibility on it.
Thanks a lot, Katie.
Thank you for your time today. It was really great.
Thank you, everyone.